What's the current flowing out of the battery now?
What's the voltage?
Oh, sorry, 12 volts.
8 amps.
What'd you say?
8.
Yes, 8. How'd you do that? There's a couple ways of going about it.
1/3 plus 1/3, 12 divided by 3 halves.
Okay, so you found the equivalent resistance first.
Yeah.
Okay. Alternatively, so one method is to find the equivalent resistance. And so the equivalent resistance is 3 halves. And then doing the exact same thing we did over there. Alternatively, you could have done a loop here. So I gain 12, I lose 12 across this one, so therefore I have 4 amperes flowing across that. I have 4 amperes flowing across that. And since I have 4 going the upper path and 4 going the middle path, I have to have 8 amperes going into it, and that's just an alternate approach. So imagine you have a series of devices which are all hooked in series. Well, let's throw a few more in there. So I got some sort of power supply, I got something there and something there, and another one, another one. So I got 5 of them there. And then another situation, I got So talk to me about the battery life in these two situations. Why don't we, just for the sake of conversation, call this series and call this parallel. Which battery is going to last longer?
I would think the series.
Yeah.
Because the amount of current has dropped significantly because I got 5 resistors there, like assuming all the resistances are the same. All right, which would have a bigger current coming out of the battery?
Parallel.
Thus it does not last as long. What would happen if one of the resistors broke in the series circuit? What would happen?
The whole circuit stops.
Yeah.
And in the second one,
Continues. Yep.
if you've dealt with Christmas lights or lights of any type, and you get that one bulb blown and you suddenly realize you have no idea, got a long strand, and which bulb is it that blew? In essence, you're dealing with series there. If you've got it all in parallel, one blows, you just see that one go out. Now, realistically, fortunately, I haven't seen that design in a while. They probably still do it, but, oh, that was a nuisance. And in parallel, you typically don't see just one bulb go out. You see a set of them, but not all of them. And so in that situation, you've got resistor, 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 and then another set here. So at least it narrows it down. You don't have the full drain of all parallel, or in that case, it's not a battery, I would assume. But you've got sort of that hybrid between the two, at least in the lights that I've seen more recently.
Is a light bulb a visual resistor? Like you can see the.
Yeah.
Okay.
So basically, as the current flows through it, there's a lot of resistance to it, and that causes it to heat up.
Okay.
And in one sense, you get to see, and another method, you get to bake something in the oven. I guess the easy bake oven was basically off the heat of a light bulb, I think.
Yeah.
Is it? Yeah, you were hesitant.
Yeah. My cousin had one. I had to change the light on it.
Okay, your cousin had one.
Yeah.
My son had one at one point. So. You ever eat anything made out of those?
It's never good
Okay.
because usually the chef that makes it doesn't have enough experience.
Oh, okay. So not a criticism of the Easy Bake Oven itself.
I haven't had anything good, but I haven't had anything made more than a 3-year-old.
There's gotta be a YouTube video out there of some adult who's tried to do that.
I know.
Alright,
They usually just use a different mix. It's the mix that makes it bad.
say it again?
It's the mix that they put in it that makes it bad. So when people do it, like, they'll use something different, their own mix.
Ah, okay. Okay.
Makes sense.
Keep it at 12 volts. Let's make the resistances up to 2 ohms, 5 ohms, 4 ohms. What's the current coming out of the power supply, and what's the current flowing across each resistor? There are multiple approaches. I want to give you a chance just to see if you can figure it out, and then we'll talk about it as a group. I'll sure grab my calculator. Answers.
I just have the one.
Okay. So you did the equivalent resistance in that, okay. Did you get the correct form across this? Oh, you just did equivalent resistance, and then, okay, so that's coming out of the power supply.
Yeah.
Would recommend at least one more decimal place. This, there, I'll get to an example later where if you round off too early, then you get some inconsistencies at the end. Oh, you have answers?
Yeah.
That's more than it should be, so you have. So that's the equivalent resistance of these two?
Yep.
Oh, you have a 12 volt drop difference from there to there. but you forgot about that one.
Okay. So after,
So it's gonna lose some across that and then lose some across that,
oh,
so.
and then, so take this number, find out the resistance of this. And
Then that'll tell you, so if you bring the two in, so that's just this piece, you bring the two into it, then you'll have equivalent resistance, and you can find the current that's flowing out of the power supply.
Okay.
And then the next part is trying to figure out how much is, well, with power supply, you got that one, figuring out how much is across those two.
Okay, so we figure this one out, and then we figure these two out. And using this, and these two.
Once you have what's coming out of the power supply.
Okay, that makes more sense. I just went 2, 5, and then 5 and 4, and add them together.
Yeah, no, it does not
That
work
does
that
not.
nicely.
I see it now.
I have a question. So,
Yeah, you did the same thing. Was that kind of different answer? You're assuming a 12-volt drop going from here to here. But there's a 12-volt drop from here to here, you have to bring the two into it. It's gonna lose some voltage going across here, it's not losing all 12 at that point. It's losing some here and then losing the rest of it there. So if you're going this path, you need to figure out the equivalent resistance. You got that, and then you have to bring two into it. And do 12 divided by that to get what's going out of the power supply. Sorry, I felt like I cut you off a couple times.
no, yeah, that's what I was gonna ask about this one. I don't have anything more.
Once you know the current's going across here, figure out what the voltage drop across here is. And then whatever's left over from 12 is what's going across there.
Yeah.
All right, so we have current flowing across here, out of here, across the 2 ohm resistor, and then it splits. I'm just gonna call this I2, I4, and I5. To figure out what's coming out of the power supply, one tack to do is to just go ahead and find the equivalent resistance. And so I've got those in parallel, so I do those first. So 1/5 plus 1/4 is equal to 1 over the equivalent resistance, which I'll just call R45. And you end up with R45 is 20/9. So we've taken that circuit and we've broken it down into, now I've got a 2 ohm resistor, and then I have a 20/9 ohm resistor. And so now my equivalent resistances, they're in series, so just add them up. So that was 2.2 repeating, so we now have 4.2 repeating ohms. So what's coming out of the power supply, again, 12 volts going across the power supply, I'm gonna lose 12 volts going across. In essence, from here to here, I'm gonna lose 12 volts, whichever path I take. And so my current would be 12 volts across, divided by 4.2 repeating, which is 1.84. 2.84, thank you. All right, so once you have that and trying to figure out the rest of it, we know what I2 is. We know what the current flowing across the 2 ohm resistor is, because whatever comes out of the battery has to flow across the 2 ohm. There's no other choice. So now we figure out what is the loss across the 2 ohm resistor, because I know what the current is. So I have 2.2 6.8421 amperes going across there. I can find my voltage drop based upon Ohm's law again. So there's my current, there's my resistance, I times R, gets me 5.6842 volts. So I gain 12 going across my battery, I lose 5.6842 volts going across here, then whichever path I take, I have to lose the rest of it. Because once I'm on the other side, there's nothing in my way. So the difference between these, so I got 12 minus 5.6842 and end up with 85137? No, 6. Did I do that math right? Somewhere around there.
Yeah.
So that has to be my drop across the 4 ohm and the drop across the 5 ohm. They're also in parallel, so they have to have the same voltage drop. Enrique?
Where did you get the change in volt, the 5.68?
Ohm's law. I know that across a resistor, the potential drop, if I'm going with the current, potential drop across the resistor is the current times the resistance. I found the current, because that's coming out of the power supply. I know the resistance it's given, so I just multiplied. Does that answer it
Yeah.
for you? Okay. So now I know I lose 6.3, I guess technically going in that direction, minus 6.3158 volts going across there. So now I have the voltage drop, I have the resistance, I can find the current. So the current 6.3158 divided by 5. 1.260316. You know, I use the calculator for a reason. Oh. One too many zeros in there. Amperes. And then for the 4, I'm going to do 4 the same way, although I do have an alternate technique, but I'm going to do 4 the same way and did 5, and then we'll use the other technique just to check it. And so here I have 6.3158 volts, drop across there, divided by 4, and 1.57895 amperes. The other check I can do here, or I could have done it this way and then checked with this equation, is my junction rule. I've got 2.8421 amps going in, I gotta have that coming out. So these two should add up to this. Hit the plus button, and I get 2.8421. And it rounds off to 1. And if we had taken this one out one step further, it would have been another 1 there. And so that's how you deal with this one. Now, there is another technique that some students will employ, but I'll save that for the moment. Questions about this one?
So once you get to those two that are in parallel, they're just a fraction of your amperage, or of your current?
They would be, yeah, some set. I mean, it'd have to be less than this.
Yeah, like I added those, like, take 5/9 of your amps and you get your I4, and you take 4/9 of your amps and you get I5.
Yeah. Yeah. Now, I mean, in essence, that works. It gets more complicated as we start adding resistors to it. And
Yeah.
so, I mean,
I see.
I've also had for people who've done some of the engineering classes of finding equivalent resistance for parallel, they said, hey, can't we just use the formula of, ultimately it's R1 times R2 divided by R1 plus R2. And yeah, that works as long as you have only two in parallel.
Right.
Once you have three, then it's R1, R2, R3 divided by R1, R2 plus R1, R3 plus R2, R3. And I'm not sure you're saving any time at that point.
Right, okay.
So, yeah, if it keeps working for you, great. But more of let's break down to the fundamentals.
Yeah.
Devon, okay. Would you like a whole mask?
You saw my real dog?
Yeah.
I'll take it. I'll try to get it together, but
They want you to have everything. See, those are gloves over there. See if we can do this without contaminating as much as we can. See if I got that pulled down. Yeah, there we go.
thank
Woo.
you.
Better than the last time I tried that.
Just had someone grab the whole side of it.
The last time I did that, somebody pulled out like 4 of them as they were going, so good. By the way, what kind of engineering are you planning to do? At this point, obviously, you're not set in stone here, but, and I would just assume in engineering, that's not always the case. What are you planning to do after this?
Mechanical,
Okay?
Computer.
Civil.
Electrical.
Mechanical.
Chemistry. So close,
Wait, 5 different things, all right. I have an engineering challenge for you, for all of you, even if it's chemistry or computers. Inspired by the cartoons, the upside down room. Somehow, I think an April Fool's Day joke is to walk into a room and everything is now upside down. Everything, so all this stuff is on the ceiling. And the reason it's an engineering challenge is how you get it to stay up there and not just fall.